pre-calc honors students. Here we are with 5.3 and 5.4, dealing with exponential functions and the number e. First, exponential functions have a standard form, which looks like this. F of x equals a times b to the x. Notice how everything's been cranked up from our linear form of y equals mx plus b. And we have two constants again, a and b. Let's see what these constants do by looking at some sliders on GeoGebra. Here in GeoGebra, I've got the basic function here, and it's actually listed here as a times b to the x, but the coefficients are sliders. So you can see that when I move a around, it changes that coefficient in front. And what does that coefficient correspond to? We'll look around on the graph here. Corresponds to that y-intercept. Because when x equals 0, 2 to the 0 is 1, so you just get that coefficient in front. So that's the role of a. Now we can also see what b is doing by sliding b around. And we get different degrees of increasing. As b gets higher, the exponential increases faster. Notice this is why we don't let the base equal 1, because we let b equal 1, then we just get a horizontal line. Not really an exponential function. We also don't have b equals 0, because if b equals 0, we just get, again, a horizontal line, the axis. Now, notice b can be between 0 and 1, and when b is between 0 and 1, we get a decreasing exponential. When b is greater than 1, we get an increasing exponential. Okay. Now, let's do some work with exponential functions. In our first example, f is an exponential function, and f of 0 equals 3, and f of 2 equals 12. Find f of negative 2. So, first, that's our standard form for any exponential, a times b to the x power. And we want to first use the idea of putting in f of 0 equals 3. So this is the point 0, 3. Put in 0 for x, and 3 for y. As a result, then, we get a equals 3. And we talked about this concept that a is the y-intercept on an exponential function. So you could have just jumped right to that and gotten to our f of x equals 3 times b to the x power. We still don't know the constant b, and we can get that by putting in the other point, 2 comma 12. So we put in 12 for y and 2 for x, and solve the resulting equation. 4 equals b squared, and b equals plus or minus 2. Now, we said before the bases have to be positive, so we're just going to take positive 2 for our base. So f of x is 3 times 2 to the x power. And now we can figure out f of negative 2 by putting negative 2 in for x, and we get 3/4. Now, there's many different variations on a times b to the x, and what you can do is replace the base with, first of all, something like 1 plus r, so you can have a growth rate. You can also vary your base, or vary the power on the base, so it can fit more seamlessly into an application problem, where a naught, or the initial amount, is multiplied by b to the t over k power, where k is the time needed to multiply by b. And we're going to see this come up over and over again in some of our application problems. For instance here, a bank advertises that if you open a savings account, you can double your money in 12 years. So express the amount of money after t years in each of the alternative forms we mentioned. Well, first we had this form, which is very handy for many applications problem. K equals the time needed to multiply a naught by b. So in this case, you double your money every 12 years. So that means in 12 years, that's our time needed k, we are going to multiply a by 2. So we can slip this into the equation then as a equals the initial amount times 2 to the t over 12. So that's one form of the equation. Now, using the other format that we talked about over here, let's see if the equation works. Now, unfortunately, the bank did not tell you the interest rate, the growth rate. We're going to have to find that out by plugging in this idea of doubling in 12 years. Doubling in 12 years. Well, how does that apply to this formula? Well, you can say the amount after 12 years is twice the initial amount. So we're going to replace a sub t with twice a sub naught. And so there's that idea of doubling. Equals 1 plus r to the 12, and 12 is the amount of time in years. So it simplifies down, divide both sides by a sub naught, and you get 2 equals 1 plus r to the 12th. 1 plus r equals the 12th root of 2, and getting out the calculator, then we get r equals the 12th root of 2 minus 1, or 0.05946. So that corresponds to 5.95% interest. What's the actual equation then in this format? Well, we can replace r with the 12th root of 2 minus 1, and we can see that this simplifies a lot, because the 1's will cancel, and we get, here's the form of the equation, a naught times the 12th root of 2 to the t. Now, compare that to what we had before, and you can see that these really are equivalent, because the 12th root of 2 is 2 to the 1/12th power, and then you end up multiplying the powers, and you get 2 to the t over 12, which is what we had back here on this page. A naught times 2 to the t over 12. Now, in this particular application problem, it seems like this was the easier way to go. So that's why I present these alternative forms of doing exponential functions that can really help you when you're doing word problems. The rule of 72 is something that's kind of handy. It's just meant to approximate, give you a quick rule of thumb for estimating how long it's going to take to double your money. And it's 72 divided by the interest rate. So as we saw over here in this problem, we ended up with an interest rate of about 6%. So that means it was going to take 6% into 72, so that's 12. So it'll take about 12 years to double your money. And indeed, that's what we saw. It doubled in 12 years. And it's only meant to be an estimate. The exact answer, depending on what approach you take and how you're compounding, is more like 0.693 or 69.3, but 72 is a number that you can much more readily go into with many percentage rates. Now let's look at example 3. A radioactive isotope has a half-life of 5 days. This means that half the substance decays in 5 days, turning into a different substance. This exponential decay, so in the next 5 days, half of what remains decays away. So half of what remains. It doesn't mean the other half goes away. So in 10 days, you have nothing left. After 5 days, you have half what you started with. After 10 days, then a quarter. After 15 days, then an eighth, and so forth. So at what rate does the substance decay each day? Well, first, let's use this format, because we're told it's halving every 5 days. So 5 days is the time needed to cut it in half. So 5 days we're going to use for K and a half for B. So there you go. The amount is the initial amount times a half to the T over 5. So that's one form of the equation, but now we're going to use that then to come up with what happens in just 1 day. In 1 day, we put 1 in for the T, and we get a half to the 1/5, and then calculating we get 0.87055. Now to think of this as a percent, this is decreasing from 1 by 0.129, or a 12.9% decrease each day. Now in 5.4 we look at a bunch of exponential applications that involve the number e and the function e to the x. E you were introduced to way back in Algebra 2 as the base of the natural logarithm. E is a number like pi. It's irrational. It's also what we call transcendental. That means it transcends the roots of a rationally coefficiented polynomial equation. So it's more complicated. I know square root of 2 is irrational as well. It's irrational, but it's not transcendental because it's the root of a simple equation like this, x squared equals 2. There's no way to get e as a root of an equation like this. E comes up so many times, though. It's defined in a very strange way here. It's defined as the limit as n goes to infinity of 1 plus n. 1 plus 1 over n, all raised to the n. So we have some conflicting things here in this formula. We put 1 in for n, we'll get 2 to the first, or just plain old 2. Now as n gets bigger, the base will get smaller, but the power will get bigger. So the power getting bigger tends to make it bigger, but the base getting smaller tends to make it smaller. These two conflict, but it seems like the power is managing to get this to increase as we go through 5, 6, 7, 8, 9, and 10. So see this gradual increasing as n gets bigger and bigger. Now, Watch what happens, though, when I start going up by factors of 10. You see that it seems to be slowing down on its rate of increase. It's approaching a limit, and this limit is the number e. Now, unfortunately, the spreadsheet I used is getting some severe round-off errors here. In fact, going over 3 at this point. These are just wrong. I'm going to zoom these out because they're wrong. It started going awry here, right around here. No. So you have to have a pretty precise calculator. Notice it asks it for all these digits, but it's not using all these digits. So on your calculator, if you try this, you might find it suddenly goes to 1. That's because it's rounding this down to 1, and 1 to any power is 1. So there's a lot of problems with trying to do these calculators with limited digits. I looked this up on Wikipedia, and here's just some of the expansion. This reminded me of something lately in the news. I want to check on that. And some kids mistakenly think that this is a repeating decimal. It looks that way for a while, 0.18281828. And in fact, let's compare that. I worked up some of these classic approximations for you. Sometimes it's a good idea to get a rough idea that pi is roughly 22 sevenths, 3.142857 repetant, but it's not equal to it. Same thing with e. You could approximate it as 271,801 over 99,990, and you'd get this 2.71828 repetant, but that's not equal to e. Both these approximations are trying to equate these irrational numbers as rational numbers, ratios to integers, but they're not. They're irrational. They keep their decimal representations, never form any patterns. Okay. So there's other ways to come up with E2. You can look at E as part of this Taylor expression, Taylor series expansion that you'll learn about in calculus. When x equals 1, you can see you can replace all the x's with a 1 and simplify that down. And write in sigma notation as well. Summation from I equals 0 to infinity of 1 over I factorial. And all those get added. The summation command, which you can get in your calc menu. And to get this factorial symbol, you can get it with diamond divide. And unfortunately, it's not labeled on your T89, but it's basically the yellow thing above the divide. Now, here's some applications. They come up in finance a lot. First, you have to understand the idea of compound interest. Here's what all the constants mean. I do expect you to memorize this formula and know how to use it. A is the amount of time t. T is the time in years. R is the annual interest rate as a decimal. N is the number of times you compound per year. And P is the principal, the amount of time. The amount of time equals 0. So here's how compounding works. How much money will have in an account after 16 years at 9% interest with an initial investment of $16,000 and compounded monthly. So if you compound monthly, that means 12 times throughout the year, you are going to get interest. You won't get as much interest as a full year, so that's why you take the interest and divide it by 12. But the effect of this should be to increase how much money you actually make. Here's the substitutions into the formula. 16,000 for the principal, 0.09 for interest rate. 12 shows up twice in the formula to both make the interest rate smaller because you're doing it more often during the year, but then the number of times you're multiplying that is increased. And that ends up with 67,000. And this is roughly on track with that rule of thumb we talked about, that at 9% interest, you can divide that into 72 and you get 8. So it'll take about 8 years to double your money. So in 16 years, we double our money twice, multiplied by about 4. Yeah, we got over 64,000. Now what happens if we compound daily? This means we're going to change the end to 365 instead of 12. On your calculators, you can just hit second entry and just edit this really quickly rather than going through all that work again. And when we calculate that, we get 60,519. So by compounding more frequently, you get a little more money. Finally, if we compound continuously, let this process go to infinity, the formula suddenly becomes much easier. Amount equals principal times e to the RT. Much easier formula. So we don't have the n anymore, and now we're using this base e. So how much money will have an account after 16 years at 9% interest, compounded continuously? So there's the formula you're going to use. 16,000 times e to the 0.09 times 16, and you end up with 67,531.13, which is just a little more, a few dollars more, $10, $20 more than what we had when we compounded daily. Flange out.